I'll start my presentation on hidden, entangled, and resonating order with a historical example of hidden order in magnetism that you're all familiar with. This is a plot of the magnetic susceptibility as a function of temperature from 1933 in an ostensibly non-magnetic material, manganese oxide. And you can see it has this characteristic to us now, lambda-shaped curve that at the time was very unexpected. So of course the behavior at high temperature was well understood by the Langevin theory of paramagnetism. When a magnetic field is applied to the disordered spins, they partially line up along the field and give a small magnetization. The cusp was indicative of a phase transition, and since the susceptibility is the magnetic susceptibility, that would suggest a magnetic phase transition, but there was no net magnetization associated with the low temperature phase, and so it was not a ferromagnet. And so there was some kind of hidden order, which of course we now know to be anti-ferromagnetism. This was proposed by Néel in 1934 and was not verified until 20 years later, when techniques of neutron diffraction had developed to the stage that they were able to verify the symmetry associated with the antiferromagnetic order. So here's the data from Schull and Smart of manganese oxide in its paramagnetic phase above the Néel temperature and in its ordered antiferromagnetic phase where the superstructure peaks unambiguously showed the antiferromagnetism. So what other kinds of magnetic order are still hidden? There's sure to be some, but where should we look for them? And today I'm going to talk about composite orders in which there's some product of order parameters that are non-zero. And the motivation for this is that perhaps all kinds of simple orders have already been founded, so they're not hidden anymore. And these composite orders can be what I call entangled, which means that they're intrinsically quantum mechanical. It's the product of the quantum mechanical wave functions that's non-zero. And they can also be dynamical. So each of the individual order parameters may be varying dynamically. So here's an example, which will be the focus of the examples that I'm going to show you, where the two order parameters are the magnetic dipole and the electric dipole, or the position operator. And of course, we are familiar with materials for which the magnetic dipole order is non-zero. These are our ferromagnetic materials in which the magnetic dipole moments are aligned. Analogously, materials for which the electric dipole is non-zero, the electric dipoles are all aligned, are ferroelectric materials. And also well established are so-called multifuroic materials, which are simultaneously ferromagnetic and ferroelectric, for which the expectation value of the magnetic dipole is non-zero and the expectation value of the electric dipole is non-zero. So there's nothing really hidden about the order in a conventional multifuroic. What I want to discuss is beyond multifuroics, but this situation where the composite order parameter, the product of the magnetic dipole and the product of the electric dipole, is non-zero, even when the expectation value of the magnetic dipole is zero and the expectation value of the electric dipole is non-zero. And so this is really providing a kind of hidden order in the material. And again, both of these quantities can be quantum mechanical or time dependent. So here's the outline. I'll start with straightforward hidden composite order of the type of product of the magnetic and electric dipole operators being non-zero. And I'll discuss the concept of magnetoelectric multipoles. I'll then give you an example of hidden quantum mechanical order, and I'll choose the example of multifuroic quantum criticality, where the product of the expectation values of the quantum mechanical magnetic and electric dipoles is non-zero. Then I'll close with a quick discussion of hidden dynamical order, and specifically the example of dynamical multifuricity. Okay, so let's start by thinking about what's the order parameter for a composite order that's the product of magnetic and electric dipole. And the answer is that the magnetoelectric multipoles that form the tensor given by the integral of position times magnetic dipole over all space are an order parameter for this kind of composite order. So this is a 3 by 3 tensor where the electric dipole can be in any Cartesian direction and the magnetic dipole can be in any Cartesian direction. It's convenient to decompose this tensor into its irreducible parts. And when one does that, one obtains what's called a magnetoelectric monopole moment. It's not a true monopole. It's in fact a second order term in the multipole expansion rather than the zeroth order term, the multipole expansion of the magnetization in a magnetic field. And that's given by the dot product of electric and magnetic dipole operators. And magnetoelectric monopoles occur when one has a magnetization texture that has this kind of hedgehog shape here. The next irreducible part of this tensor is the magnetoelectric toroidal moment. This is a vector given by the integral of position cross product with magnetic dipole, and this corresponds to swirls of toruses of magnetization. And the final 5 components of this tensor are the magnetoelectric quadrupole moments, which are the same as the magnetic quadrupole. So the motivation for understanding these magnetoelectric multipoles is given by the linear magnetoelectric effect, in which one applies a magnetic field and induces an electric polarization that's linear in the magnetic field, or conversely, the application of an electric field induces a magnetization. And the coupling between these cross effects is the magnetoelectric tensor, and one can see immediately from this form of the equation that it's non-zero only in the absence of both space inversion and time reversal symmetry. And one can be more detailed and recognize that the form of the tensor is determined by the details of the structural and the magnetic symmetry. And in fact, one can show that the existence of magnetoelectric multipoles, which order ferroically, correlates with a non-zero linear magnetoelectric tensor and vice versa. And in particular, if one has a system that's purely consists of a hidden order made of magnetoelectric monopoles, one has an isotropic and diagonal magnetoelectric tensor. Magnetoelectric toroidal moments correspond to an antisymmetric and off-diagonal tensor, and the quadrupoles yield a traceless magnetoelectric tensor. So let's look at an example, which is chromium-203. So chromium-203 is the prototypical magnetoelectric material. Here's just a sketch of the known common magnetoelectric materials, and it's kind of in the middle as a function of its magnetoelectric, linear magnetoelectric coefficient. It's not particularly, doesn't have a particularly high magnetoelectric response. It was the first material in which Igor Jalashinsky proposed the magnetoelectric effect. He showed that it was required to show one by symmetry, and he also showed that it's uniaxial with alpha 1,1, the magnetoelectric response along the symmetry axis, in the plane, equal to alpha 2,2, and different from alpha 3,3, which is the uniaxial symmetry axis. And so the magnetoelectric response can be written as the sum of a monopolar part plus a quadrupolar part. And if we look at the magnetic structure of chromium-203, it has these strings along the z-axis, along the direction 3, consisting of magnetic moments that are also oriented along the z-axis, pointing towards each other in pairs. And you can just, in a cartoon, rewrite this magnetic order like a monopole structure plus a quadrupole structure. And so we expect, again, a magnetoelectric monopole, and we see that this is the z-squared quadrupole. So we can calculate the magnetoelectric monopoles in materials. This is the work of Florian Törler, who was a PhD student in the group, and Michael Feschner, who is now a postdoc in Hamburg in the Max Planck Institute. And one can calculate the local magnetic moments, for example, at the chromium sites, just by integrating the position times the magnetic dipole. And when we do that, we find that on the chromiums, they're all non-zero, and they all have the same sign. It's a ferromonopolar material with this hidden magnetoelectric monopolar order. The units, of course, are magnetization times position, which is more Bohr magnetons, angstroms, for example. One can also convert this local magnetoelectric monopolization at the atomic sites into a bulk monopolization, a monopole moment per unit volume, and get a number which is this value divided by volume, so it's Bohr magnetons per square angstroms. And again, this is non-zero, consistent with the magnetoelectric response of chromium-203. If you look at these units, this is it's a bulk thermodynamic quantity. It's a magnetization times position divided by volume. But we see also that these units are magnetization per unit area. And one can see then just intuitively from the magnetization, from the units, that one should associate a surface magnetization with the presence of a bulk magnetoelectric monopole. And one can actually show this rigorously, that associated with a magnetoelectric antiferromagnet that has a net magnetoelectric multipole, there's an intrinsic surface magnetization that arises from the bulk magnetoelectric behavior, and that does not occur in an ordinary antiferromagnet that doesn't break the space inversion symmetry. And so for chromium-203, we can also calculate this quantity. Because there is a monopole and a quadrupole, one finds that there's just a Z component of the surface magnetization, and one can extract a number which comes out to be a measurable number, 2.4 Bohr magnetons per square nanometer. And there's quite some activity at the moment in trying to measure this value at domain walls, domain boundaries, using NV center magnetometry. I want to tell you briefly about a project that I enjoyed very much, in which we tried to measure this hidden magnetoelectric monopole in chromium-203. This was the master's thesis project of Quintin Meyer, who subsequently did his PhD in the group and is now a postdoc in Grenoble, and in collaboration with Igor Janoshinsky, who sadly just passed away just last week, just after his 90th birthday. So one can show, if one has a chromium-203 slab, an infinite slab, which is occupying the entire half plane, and one puts a charge, a real electric charge, on the surface of the chromium-203, then this electric charge, of course, induces an image charge in the chromium-203, which, because of the magnetoelectric response, creates an image monopole. And this image monopole, the red arrows here are showing the magnetic field associated with this image monopole. Above the surface in the vacuum, the magnetic field associated with this image monopole is perfectly monopolar. So you see that these red arrows are converging onto this point. Again, also you see it's not a true monopole. There's no divergence of the magnetic field. These field lines don't reach the point. But it creates a perfectly monopolar field in the vacuum. One finds this just by solving Maxwell's equations, but including the cross-coupling terms that an electric field induces magnetization and vice versa. So how to measure this? It's kind of a fun prediction to have a prediction of a purely monopolar external field. And to emphasize again, there is no magnetic charge. It's not a real monopole, and B does not really diverge. So the idea that we had was to try to detect this magnetic field using muon spin resonance. And so this project the experimental part of this project was led by Hubertus Lütkens at the Paul Scherrer Institute, again with Michael Fechner and Quintin Meyer. So the idea is that one sends in a muon, which stops in some dielectric above the surface of the chromium-203. And the muon, of course, is charged. And so it provides the charge, which creates the image monopole. So this is our slab of chromium-203. The muon is also a sensitive magnetic field detector, and so it's able to detect the magnetic field at the point where it stops. And so if one converts the sketch I showed you earlier of the red arrows showing the magnetic field into an actual predicted magnetic field as a function of implantation depth above the chromium-203 surface, so this is the surface here and this is distance from the surface, one sees the exact monopolar form of the magnetic field. Let me show you then for comparison what we measured. So here's the measured magnetic field as a function of the muon energy. So high energy muons are close to the chromium-203 surface and lower energy muons are further away. And you can see that the measured field is at least not inconsistent with the monopolar predicted behavior, but we certainly can't say for sure that we actually measured one. So we wrote a nice paper saying explaining how we searched for the magnetic monopole at the surface of the magnetoelectric. But it's, I'd say, this measurement, this definitive measurement of this behavior is still an open question. There was a very nice article in Ars Technica. This is my lobbying for open access publishing, because then editors in popular magazines read your papers saying a funky mirror turns electric field into a magnetic field with missing pole. Before I move on to the next topic, I want to mention one other behavior. So I've been discussing so far this hidden ferromonopolar ordering that creates the magnetoelectric behavior in chromium-203. Iron-203, Fe203, has the same crystal structure as chromium-203, and in its low temperature phase, it has also its spins oriented along the Z direction, but instead of the down-up pattern of the chromium-203 spins, it has a down-up, up-down pattern. This pattern, this magnetic ordering, doesn't break this base inversion symmetry, so it's not magnetoelectric, but locally it still has magnetoelectric multipoles. And if one looks at the monopolar component, one sees that one has two monopoles of one sign and then two monopoles of the other sign. So application of an electric field to Fe203 in this phase does not cause a net magnetization, but it causes a local magnetization. So we have a hidden anti-ferromonopolar order. The bulk monopolization is 0, but this behavior should manifest as a non-zone center magnetoelectric response. If we apply a spatially varying electric field, that should induce a homogeneous magnetization. And notice that the pattern of the anti-ferromonopolar order, it's like plus, plus, minus, minus, is different from the dipolar antiferromagnetic order, which is down, up, down. Okay, so I'm going to collect a to-do list throughout my talk rather than really a summary. And for sure, I'd say an unambiguous identification of a magnetoelectric multipole with the product of its magnetic and electric dipole non-zero in a case where the magnetic dipole is 0 and the electric dipole is 0 is still to be done experimentally. Let me move on to the second topic. The second and third topics will be rather shorter and discuss how such a hidden order can be quantum mechanical and talk about multifuroic quantum criticality. So now we're interested in the quantum mechanical wave functions associated with the magnetic dipole and the electric dipole being non-zero. So of course, we're very familiar with magnetic quantum criticality, where the magnetic phase transition between, say, a paramagnetic and a ferromagnetic phase, instead of happening as a function of temperature, which is what happens in a conventional phase transition, they happen as a function of some control parameter, which could be, for example, strain or magnetic field. And the transition, when it occurs at 0 Kelvin, is called the quantum critical point. The transition from the ferromagnetic to the paramagnetic phase is driven by quantum fluctuations rather than thermal fluctuations. There's an analogous ferroelectric quantum criticality in which the transition from the paraelectric disordered electric dipoles to the ferroelectric ordered dipoles, instead of occurring as a function of temperature, again occurs as a function of some control parameter, which could be electric field, which could be strain. And the quantum critical point is the point separating the ordered and the disordered phases at 0 Kelvin. An example of where this occurs is in strontium titanate, where the control parameter is substitution of a heavier ion. So conventional strontium titanate with oxygen 16 is a ferroelectric. It's sitting on this side of the quantum critical point. But if one substitutes strontium 18, oxygen 18, so that the ions are heavier, then it's a ferroelectric material. One can also make this transition in conventional strontium titanate with strain. And this was this ferroelectric quantum critical behavior was really confirmed about 7 years ago by Rowley and co-workers, who measured the dielectric constant as a function of temperature, and they found the characteristic behavior that the inverse dielectric constant is linear in T squared over rather a wide temperature range up to about 70 Kelvin above the quantum critical point. So what we were interested in was, could we couple quantum critical points in which one of them was a magnetic quantum critical point and one was a ferroelectric quantum critical point, and make multifuroic quantum criticality? And if we could find a material that in which we could realize this, then what would it do? And so this was the work of Abhadesh Narayan, who's now an assistant professor at the Indian Institute of Science, in collaboration with Anders Kano and Sasha Belatsky. So our thought was that with some control parameter, we should first identify a material that would have both a magnetic quantum critical point and a ferroelectric quantum critical point. And with some control parameter, maybe we could tune them and bring them together, and maybe there'd be some new order, maybe there'd be a room temperature superconductor or some exotic behavior associated with the interaction between these quantum critical points. So the material system that we identified where we think this should be observable is europium titanate. It's very similar to the strontium titanate, in which ferroelectric quantum criticality was invented, but instead of strontium, it has europium, which of course has a large magnetic moment from the F electrons. So it's known to be an antiferromagnet with a rather low Néel ordering temperature, and to be believed to be a quantum paraelectric, and it has a very large dielectric constant at low temperature. And so what we found computationally is that when one substitutes strontium for europium, the magnetic ordering is suppressed by diluting, but the ferroelectricity is not affected. Strontium and europium are very similar in size. When one substitutes barium for strontium, one suppresses the magnetic ordering, but enhances the ferroelectricity because of the larger size of the barium. And so one can make a phase diagram for the europium barium strontium titanate system. Is the temperature as a function of the barium concentration, as a function of the strontium concentration, and the green line is showing the Néel temperature being suppressed by barium doping, and the blue line, the ferroelectric Curie temperature being enhanced with barium doping, and then the same variation with the strontium doping. And so you can see one can tune by varying the concentrations of europium, barium, and strontium one's point in this phase diagram, and vary the distance between the quantum critical points. We can also calculate how the susceptibility should be affected by the spacing between the quantum critical points. And if one sits close to the ferroelectric quantum critical point, where the inverse susceptibility is proportional to T squared, and move the magnetic critical point closer, the susceptibility crosses over and is dominated by the lower exponent, and one should see a crossover from T squared to T to the 3/2 behavior. So this has not been done yet. It would be very interesting to verify experimentally the signatures of multifuroic quantum criticality in the critical scaling, and also still to be done both theoretically and experimentally, is to see what kinds of interesting behaviors this will lead to. If you're interested in crossovers in susceptibility, it already is predicted to show an interesting behavior, but maybe it will also show something else. Okay, so in my last 5 minutes, let me very briefly tell you about, just to taste of hidden dynamical order in the context of dynamical multifuroicity. And here I build on the well-established physics of magnetically induced ferroelectricity, in which a curl of the magnetic order gives rise to a polarization. Here you can see that the spins are lifting the inversion center, and this gives an electric dipole. There's an analogous polarization-induced magnetism, but in this case, it's the time derivative of the polarization, which gives a magnetization. So a time-varying electric dipole gives a magnetization. One can see this in the comparison between the free energy. Magnetization-induced polarization has a term in the free energy of P dot M cross curl M, which leads to a polarization given by M cross curl of M. And the polarization-induced magnetization has a term in the free energy M dot P cross dP by dt, which gives a magnetization proportional to the polarization cross dP by dt. So this is the work of Dominik Jurasek, who's now a postdoc at Harvard and is about to start his independent faculty position in the physics department at Tel Aviv, again with Michael Fechner and Sasha Polansky. So I want to give you just one example. We predicted many behaviors that would result from this phenomenology, but the one example I want to give you is that the optical phonons should cause a magnetism. So in an optical phonon, the positive and negative ions move in opposite directions. And if one can just see intuitively that if one excites perpendicular optical phonons and they're out of phase with each other, then the ions move around in loops. And ions of opposite charge, of course, these ions are charged, they're going around in a circle, and so there's a magnetic moment associated with them. Ions of opposite charge have opposite signs of this magnetic moment, but in general, these are not going to cancel out, and one ends up with a net magnetization. And so associated with this excitation of the phonons is a Zeeman effect. A pair of degenerate out-of-phase phonons has a constant magnetization, and the sign of the magnetization is opposite for opposite relative phase of the excitation. And so one predicts a Zeeman splitting in an applied magnetic field. So if the phonons start with some frequency omega 0 in the absence of the magnetic field, one of the circular polarized phonons will shift to lower frequency and one to higher frequency. So is this measurable? Well, for strontium titanate, we find that the low frequency, for the lowest frequency phonon modes, or doubly degenerate phonon modes, they have to be degenerate at about 1 terahertz. This proportionality constant is about 10 to the 6 per Tesla per second. And this gives a relative splitting, which is very small, about 10 to the minus 3 in a field of 55 Tesla. So this is, I think, maybe in principle accessible, but right at the limit of what could be measured. So I add this now to my to-do list to measure the phonon Zeeman effect. We made a paper with a zoology of many materials and calculated the orbital magnetic moments of them for a range of ceramics. Unfortunately, it seems that strontium titanate is the most favorable, but we continue to look for other more kind of floppy materials in which this effect might be enhanced. So let me summarize then. I hope I've convinced you that composite orders of the kind magnetic dipole times electric dipole non-zero can form a kind of hidden order in magnetic non-centrosymmetric materials. Can they be measured? I showed you an example where we almost but not quite measured them with muon spin resonance spectroscopy. I proposed some quantum scalings and a phonon Zeeman splitting, which might allow them to be measured. Could they be useful? I have no idea. I hope that maybe some of you have some ideas of perhaps some exotic Monopole electronics or some kind of novel storage that they could be useful for. So thanks for listening, and I'd be very happy to take any questions or comments.